Hello and welcome to Meduhub. I am Neha Gupta, a part of our chemistry faculty, and today we will be talking about aromatic monocyclic hydrocarbons. Till now we have studied about alkenes, alkanes and alkynes. They are straight chain compounds and they are called aliphatic compounds. Now we have to study about aromatic ones. So what is the difference between the two? So initially in the early days of organic chemistry, the first compounds to be isolated and studied were fatty acids. In Greek, aliphos means fat. So they were called fatty acids and they were straight chain compounds. Nowadays, aliphatic is a term used for any open chain structure. So aliphatic compounds are open chain compounds. Apart from these, a lot of compounds were isolated from natural sources like resins, essential oils. They were different from aliphatic compounds and all of them had one thing in common. They had a very pleasant odor. So, arbitrarily, these compounds were kept in a category called aromatic compounds. Aromatic. Because in Greek, again, aroma means a pleasant odor. So these aromatic compounds were found to have a higher percentage of carbon than their corresponding aliphatic compounds. That means they had a higher degree of unsaturation. And whenever these aromatic compounds were subjected to some treatments, they always gave benzene or its derivatives as the products. So aromatic compounds was reserved for all the compounds which were either benzene or its derivatives. So aromatic compounds were also called benzenoids. Nowadays, these aromatic compounds have a cyclic structure in which 6 carbon atoms are arranged in a ring, that is benzene, and then its derivatives have other substituents attached to it. Nowadays, many more aromatic compounds are known, and if they do not contain a benzene ring, they are called non-benzenoids. So we have benzene, for example. We can say we have an NH2 group attached here which is called aniline, or we have chlorobenzene. Then there is another compound in which 2 benzene rings are fused together. This is called naphthalene. And so on. Next, we need to see what is the structure of benzene. So we'll talk about the structure of benzene. The molecular formula of benzene is C6H6. Now this formula does not correspond to any of the formulas that we have studied for alkanes, alkenes or alkynes. It does not fit into that general formula. So what kind of structure will you suggest for benzene? And it was a subject of deliberation for many years. It was found that benzene forms a triozonoid. This is the reaction that we have studied in alkenes, where a double bond adds on a molecule of ozone. So since it formed a triozonoid, it means it has 3 double bonds. Also, it was found that it only formed one monosubstituted product. Only one monosubstituted product. This means that there are 6 carbons in benzene and all of them are equivalent. So all 6 carbons are equivalent. So Kekule suggested a structure in which the 6 carbons formed a ring and there were alternating double bonds, and here there are hydrogens. Now if we number these 1, 2, 3, 4, 5, 6 and we have a di-substituted product of benzene. So we can say either that, let's say a bromine is getting attached to benzene. So let's say that bromine can either be attached to carbon 1 which has a double bond with carbon 6, or it can be attached to carbon 2 which has a double bond with carbon 3. But it was found that it only formed one type of ortho. Ortho means adjacent di-substituted product, which means that these double bonds have an oscillating nature. So either the double bond can be like these between carbon 1, carbon 6, carbon 5, carbon 4 and carbon 2, carbon 3, or we can draw another structure where the double bonds are like this. So if we again number them 1, 2, 3, 4, 5, 6. Here the double bonds are between carbon 1 and 2, 3 and 4, 5 and 6. So benzene is actually a resonance structure of these two contributing structures, and we can draw it like this. Or a circle. So in benzene, what happens is every carbon is sp2 hybridized. Okay, so these sp2 hybrid orbitals form a head-on sigma bond. We'll talk about this carbon first. So this carbon forms a head-on sigma bond with this carbon, another sigma bond here with this carbon, and a third sigma bond here with this hydrogen. Similarly, all of these are sigma bonds, and there's another sigma bond with the hydrogen. Now, the unhybridized p orbital of every carbon contains a pi electron. This pi electron has equal probability to form a partial overlap, a sideways overlap with either the pi electron of this carbon or the pi electron of this carbon, right? So it has been found that all the carbons of benzene are equivalent, and all these bond lengths, whether it is a carbon-carbon double bond or a carbon-carbon single bond, all these bonds are the same length, and they lie between the bond length of a carbon-carbon single bond and a carbon-carbon double bond. So these pi electrons are delocalized over the entire ring. So if we draw this ring like this, these are the pi orbitals. They are delocalized, and there is equal probability of forming a bond here. So this means that there is an electron cloud. If benzene is in a plane, it is a planar structure, there is an electron cloud above the plane of the ring and below the plane of the ring. This means that benzene is an electron-rich species, and this is the reason that benzene has very unusual properties, and despite having 3 double bonds, these double bonds do not act as pure double bonds. They do not undergo addition reactions like alkenes. They rather prefer to undergo substitution reactions, and more specifically electrophilic substitution, because electrophilic is electron seeking or electron deficient. So an electrophile tends to attack the benzene ring, and benzene undergoes substitution rather than addition. Though under extreme conditions it does undergo a few addition reactions, but the reactions of an aromatic compound are entirely different from that of an aliphatic compound. Alright, next we need to talk about how is it that we define aromaticity and the Huckel's rule. So compound is said to be aromatic if it has unusual stability, which is usually associated with a large resonance energy, it shows unusual properties, that is, it prefers substitution rather than addition, it has a complete delocalization of pi electrons, and fourth and very important is that it has almost a planar structure, a reasonably planar structure with the presence of 4n plus 2 pi electrons in the molecule. So where n is an integer, it can be 0, 1, 2, 3. This 4n plus 2 pi rule is called the Huckel's rule. Let us see a few examples to see how you can calculate the number of pi electrons, and through this Huckel's rule you can figure out if a compound is aromatic or not. So the first one we have is benzene. These are the pi electrons, 1, 2, which are, these bonds are formed by sideways overlap. So there are in all 6 pi electrons. So 4 to n plus 2 is equal to 6. This gives 4n is equal to 6 minus 2, 4. N is equal to 0. N is an integer, that means benzene is aromatic. Now if we look at naphthalene here, let's count the pi electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 4 into 10 plus 2, 4 into n, 4n plus 2 is equal to 10. 4n is equal to 10 minus 2, 8. N is equal to 2. Hence, naphthalene is also aromatic. Now, here we have pyridine. So, pyridine has 1, 2, 3, 4, 5, 6 pi electrons. This lone pair of electrons belongs to the s orbital. It is not, these are not pi electrons. So, pyridine has 6 pi electrons. Again, 4n plus 2 is equal to 6. 4n is equal to 4. N is equal to 1, and hence pyridine is also aromatic. Now we have furan. It has 1, 2, 3, 4, 5, 6. Now the other lone pair on the oxygen atom is again from the s orbital, and it is not pi electrons. So we have total 6 pi electrons. 4n plus 2 is equal to 6. 4n is equal to 4. N is equal to 1. That means furan is also aromatic. Here we have a cyclopropanyl cation. Cyclopropanyl cation has 1 and 2 pi electrons. 4n plus 2 is equal to 2. 4n is equal to 0. This means n is equal to 0. So this one is also aromatic. This way, if you are given any other compound, you can calculate the total number of pi electrons and then put it in the formula where an aromatic compound has 4n plus 2 pi electrons, and find out if n is an integer. That means that the compound will be aromatic. Otherwise, in some cases, if you say n is a fraction probably, then it is not aromatic. So that is the Huckel's rule, and it's a very important topic from your NEET point of view, because a question came in the 2023 NEET as well. So you need to practice a lot of questions and then understand how to calculate the number of pi electrons and determine the value of n, and hence determine the aromaticity, right? So we have studied the difference between aliphatic and aromatic. We have talked about the structure of benzene and how it has resonance stability, aromaticity and Huckel's rule. Now let us see what kind of isomers are possible for benzene. Just a second. Isomerism. So all the derivatives of benzene which have an alkyl group attached to it are called arenes. Now if we have benzene and have a monosubstituted derivative where we have CH3 attached to it, since all the carbons of benzene are equal, there is only one monosubstituted derivative possible. So there is no isomer possible for this. This is called toluene, or we can also call it methyl benzene. But what happens in the case where we have a di-substituted derivative of benzene? Here and here. So there are three possibilities now. If the first group is here, the second group can either be here, or this group can be here with respect to the first group, or this group can be here. So these three possibilities are there because if we number the carbons 4, 5, 6, with respect to carbon 1, position 2 and position 6 are equivalent. Again, with respect to carbon 1, position 3 and 5 are equivalent, And the third possibility is with respect to carbon 1, the other substituent is at carbon 4. So the first possibility where there are adjoining groups present, adjacent groups present, this isomer is called an orthoisomer, where the substituents are present at carbon 1 and carbon 3 are called meta isomers or meta ortho, or here where the substituents are present at carbon 1 and carbon 6 is called the para isomer. So to take an example and understand this better, let us take a compound which has 8 carbons and 8 hydrogens, C8H8. How will you draw the structures of these? So it is an aromatic hydrocarbon. How will you draw the structures of the isomers? First we will draw the benzene ring. 6 carbons are accounted for. There are 2 more carbons. Either they can be present as methyl groups here, or these 2 methyl groups can be present meta to each other, or third possibility, these 2 methyl groups can be present para to each other. Apart from these, there is a fourth possibility also where these 2 carbons are present as an ethyl group on benzene, making it a mono-substituted derivative. So C8H8 will have 3 position isomers and 1 more isomer, which will be the basic difference in the carbon skeletal structure or a chain isomer. So here this is called xylene, where 2 methyl groups are present on benzene. Since they are ortho to each other, this will be called orthoxylene. Here they are meta to each other, so it is called metaxylene. Here they are para to each other, it is called paraxylene. And this one is ethyl benzene. Alright, let us see the nomenclature. We have briefly discussed it because we know if there is one substituent, we just name the substituent followed by benzene. So we have an ethyl group here, it's called ethyl benzene. If we had a methyl group here, this is methyl benzene. Let us look at a few more examples. Here we have a bromo group on benzene. This will be called bromobenzene. Bromobenzene is one word. Here NO2 group is present, which is a nitro group. This is called nitrobenzene. Now look at this example. Here we have a bromine here, atom here, and a chlorine atom here, a bromo group and a chloro group. Here you start numbering just like you do in aliphatic compounds. So we can number 1, 2, 3. Okay? Or we can start from chlorine as well because both are substituents. 1, 2, 3. You see that both of them are getting the same set of locants, 1 and 3 or 1 or 3 with respect to each other. What do you do in such cases when the set of locants is the same? So you cannot follow the lowest locant rule because the locants are the same. In this case, you go alphabetically. So since B comes before C, we will start numbering from bromine and we will write 1 bromo hyphen 3 hyphen chloro benzene. Alright, chlorobenzene will be one word. Now look here. Here again we will start numbering. Nitro group and chloro group both are substituents. So we will start numbering 1, 2, 3, 4. Or we can start numbering from this side also. 1, 2, 3, 4. Now see, from one side the locant is 1, 3, 4. If we start numbering from here, 1, 3, 4, otherwise it is 1, 1, 2, 4. This is the lowest locant. Hence, we'll start from here. So this will be 1 chloro, 2, 4 dinitro benzene. Alright, this follows the lowest locant rule. In this example, again we'll start numbering 1, 2, 3, 4, or we can start numbering from this side also 1, 2, 3, 4. So the locant here is 1, 2, 4, or this side is 1, 3, 4. That side gives us the lowest set of locants, so we'll start from there. We have fluoro, we have nitro, we have ethyl. Now, again, apart from the lowest locant rule, we have to see the alphabetical order also. So this is F, this is N, this is E. E comes first, so we will write 4 ethyl. After E, we'll have F, 1 fluoro, 2 nitro benzene. Alright, let's see some more examples. Here, prima facie, if we look at it, you can say this is an orthoxylene which is substituted with bromine at the 4th carbon. So you can also write it as a bromo derivative of the trivial name which is orthoxylene. So this can be 4 bromo orthoxylene. There's no space here. 4 bromo orthoxylene, or you can start numbering 1, 2, 3, 4. So this will be 4 bromo, 1, 2 dimethyl benzene. If you look at this example, one way is to start numbering 1, 2, 3, 4. Why did we start numbering from chlorine? Because C comes before M alphabetically. So this will be 1 chloro, 4 methyl benzene, or again we know that if benzene is substituted with CH3 group, this is the common name is toluene. So this can also be written as a chloro derivative of toluene. So we can write, in case we are writing it as a chloro derivative of toluene, methyl group has to get number 1 because we are taking toluene as the parent hydrocarbon here. So we'll have 4 chloro toluene. Alright. Here we have an NH2 group here. Benzene substituted with an NH2 group is called aniline. NH2 is a functional group. So we start numbering from here 1, 2, 3 and 4. This is aniline which is substituted with nitro group at 2 position and a methyl group at the 4 position. So we will write 4 methyl, 2 nitro aniline. Alright, the structure of aniline, just for clarity, is this. NH2. Now, we'll do this later. Look at this one. Here, an OH group is attached to benzene ring here. OH is a functional group, and when OH is attached to benzene, this is called phenol. Alright, so this is the functional group. We start numbering from here 1, 2, 3 and 4. So this will be 3, 4 dimethyl phenol. So whenever a functional group is present, that is given priority over all the other substituents, because you need to know that the nitro group, alkoxy group like a methoxy group, or all halogens or a phenyl group sometimes are always substituents. And you already studied about the types of functional groups that there are. Now look at this example where the benzene ring is not the parent ring, but it is a substituent here. So in the cases where an alkyl chain is attached to a benzene ring and that alkyl chain is substituted, in that case, this will be taken as a substituent and not as a parent hydrocarbon. So here we start numbering 1, 2, 3, 4, 5 and 6. So this will be 3, 4 dibromo, 6 phenyl, and what is the parent hydrocarbon here? It is a 6 carbon alkane which is called a hexane. So 6 phenyl hexane. Right, so this is an example where the benzene ring is a substituent. So the univalent group that comes out of taking a hydrogen out of benzene is called a phenyl group. Just like we studied alkyl groups and alkanes, it is similar to that. So one hydrogen is replaced by this alkane here and benzene becomes a substituent and it is called a phenyl. Alright. Next we need to see the physical properties. So benzene and all the other arenes are colorless, liquids or solids. They all have a characteristic odor. This we have already studied, and they are non-polar. Since they are non-polar, it implies that they are not soluble in water and they are soluble in all other organic solvents. They all burn with a sooty flame. And this is a combustion reaction which is sometimes used to distinguish between an aliphatic and an aromatic compound. So if you burn an aromatic compound in the lab, you will see it always burns with a sooty flame, whereas an aliphatic compound will not. So this is important that way from the practical point of view. And apart from that, if we talk about the boiling point, so with each addition of a CH2 group in arenes, what happens? The boiling point rises fairly regularly. And if we talk about isomers, their boiling point is fairly close together or fairly the same. So these are the physical properties of the aromatic compounds that you study. After this, we need to see how we can prepare benzene and other arenes. Next is preparation. The first method is cyclic polymerization of alkynes. So this we have studied already in alkynes. If we have ethyne, if you take three molecules of ethyne and you pass them over a red hot iron tube, they cyclize and form benzene. Right? And they'll give hydrogen. What if we have a propyne? So this was ethyne, red hot iron tube. If we have propyne, we'll have CH3, C, CH. If we take 3 molecules of this and over similar conditions, this will give us an arene which is tri-substituted benzene with methyl groups here. Alright, how will you name it? We'll start numbering 1, 2, 3, 4, 5, 6. This will be 1, 3, 5 trimethyl benzene. Okay, Next reaction is the hydroforming process. Hydroforming involves cyclization, dehydrogenation and isomerization of an alkane to give an aromatic compound. This is a reaction that you have again studied in alkanes. We are just going to repeat it here. So if we have N-hexane, for example, N-hexane, and around a temperature of 400 to 500 degrees Celsius, if we use Cr2O3 over alumina, this will give us benzene and 4H2. So these 6 carbon atoms will cyclize, they will lose hydrogen and they will give us benzene plus hydrogen. If we have N-heptane, so that will be CH3, then the CH2 group and CH3. Over similar conditions, this will again cyclize, lose hydrogens and give us toluene, a methyl group here. So this is toluene. A very interesting reaction is when we use N-octane. So we have N-octane that will have CH3, CH2, 6, CH3. Now these 6 carbons will form benzene, and apart from that we'll have 2 carbons remaining, because in a hydroforming process the final aromatic compound we get always contains the same number of carbons as the starting aliphatic compound. So here we had 6 carbons, we got a benzene. Here we had 7 carbons, so we got a benzene with 6 carbons and another carbon as a methyl group here. So the number of carbon atoms remains the same. If we take N-octane, it is very interesting. Over similar conditions, 6 of the carbon atoms will form benzene. We'll have 2 carbon remaining. They can form xylene. Now we have studied that xylene can have 3 isomers, and with 8 carbon atoms we have another isomer as well. So this will give a mixture of orthoxylene, paraxylene, metaxylene and ethyl benzene, C2H5. So this is an example of the isomerization process that we spoke about. So in hydroforming, dehydrogenation takes place, cyclization takes place. So dehydrogenation takes place here. In this example, cyclization took place and we got a methyl group. In this example, we got isomerization as well. So we have these 4 isomers of C8H8 that we receive. This is the hydroforming process. Next is the decarboxylation of aromatic acids. The third method is decarboxylation of aromatic acids. So if you take a sodium salt of benzoic acid, COONA, and you treat it with soda lime, which is a mixture of NaOH and quicklime, CaO, upon heating, it will lose a molecule of CO2 and we will get benzene and sodium carbonate, Na2CO3. Similarly, if this is how to prepare benzene, if we have this, a CH3 group here as a substituent, this is called para-toluic acid. This, when treated with soda lime, it gives us toluene as the product. So a molecule of CO2 will be removed and we'll get CH3 here plus sodium carbonate. This toluene, this benzene. Alright. The next and the last method is from phenol. So if you pass phenol vapors over zinc dust, this is phenol, OH group here, over zinc, we get benzene. The yield is not very nice in this reaction, but this is the fourth method that you have to study. Okay, now we need to see what chemical reactions benzene undergoes. So we have established that benzene has a rich electron cloud above and below its plane. So it undergoes electrophilic substitution reactions. Apart from this, the second type of reactions that benzene undergoes under special conditions is addition reactions, and benzene also undergoes oxidation, which is a combustion reaction when burnt in air. So one by one we will tackle all of them. Let us first talk about electrophilic substitution reactions. Electrophilic substitution reactions. An electrophile is a species that is electron deficient and it seeks electron rich nucleus. So here a hydrogen atom of benzene is replaced by an electrophile and hence it is called electrophilic substitution reactions. The first electrophilic substitution reaction that we are going to study is nitration. In nitration, a hydrogen of benzene is replaced by a nitro group. So if we treat benzene with a mixture of concentrated HNO3 and concentrated H2SO4, we get nitrobenzene. Next is halogenation. Halogenation, that is replacement by a halogen atom. So if we talk about chlorination or bromination, we have benzene. We treat it with chlorine in the presence of a Lewis acid like anhydrous AlCl3. We will get chlorobenzene. And HCl. If we treat benzene with excess of chlorine in the presence of anhydrous AlCl3, we will get a hexa substituted benzene. Chlorine, chlorine and chlorine here. This is called hexachlorobenzene. And similarly for bromination, if we treat benzene with bromine in FeBr3, we will get bromobenzene. Now since iodine is the least reactive of all the halogens, direct iodination is also not possible. So it is carried out in the presence of oxidizing agents like HNO3, the detail of which we will study in haloarenes. Similarly, fluorine is highly reactive. So direct fluorination of benzene is also a problem and it is explosive. So indirect methods are used for fluorination, which we will again talk about in haloarenes. For right now, the substitution reaction in benzene is for chlorine as bromine. So we will just study about chlorination and bromination here. We will talk about iodination and fluorination later on. So the next reaction is sulfonation. Sulfonation. Sulfonation means replacement by a sulfonic acid group, SO3H group. Sulfonation is carried out when benzene is heated with fuming sulfuric acid. So it's H2SO4 SO3, which is also called oleum, H2O7. When benzene is treated with fuming sulfuric acid, we get benzene sulfonic acid. The fourth one is a very important reaction called the Friedel-Crafts reaction. Friedel-Crafts, we'll talk about Friedel-Crafts alkylation and acylation. So let's talk about alkylation first. Friedel-Crafts alkylation reaction. In Friedel-Crafts alkylation reaction, an alkyl group is substituted on benzene. So if benzene is treated with an alkyl halide in the presence of a Lewis acid like aluminum chloride, we get toluene as the product or an alkyl benzene as a product. Benzene treated with CH3Cl, which is a chloromethane, in the presence of anhydrous AlCl3, we will get benzene substituted with a methyl group here, this is toluene. Similarly, if we use CH3CH2Cl in AlCl3, we will get ethyl benzene as the product. So we can summarize this as benzene reacting with an alkyl halide in the presence of anhydrous AlCl3 to give alkyl benzene and HCl. Now Friedel-Crafts reaction has some drawbacks. The first one is, it is very easy to prepare a methyl benzene or an ethyl benzene and even an isopropyl benzene. The problem comes when you try to introduce an N-propyl or an N-butyl group. So what happens if you treat benzene with an N-propyl halide, that propyl group rearranges to give an isopropyl group, right? So that isopropyl carbocation that is forms isopropyl benzene. And in the case of N-butyl group, what happens that N-butyl group gives isobutyl group, which further gives a third butyl group. To introduce a straight chain 3-carbon alkyl group or a 4-carbon alkyl group is a problem in using Friedel-Crafts reaction. So that is overcome by treating N-propane. I'll just draw this here. So we have benzene, we have CH3, CH2, CH3, CH2Cl, chloropropane in the cold. If the reaction is carried out in the cold, in the presence of anhydrous AlCl3, that's when a straight chain propyl groups get attached. If this reaction is carried out at high temperature, then an isopropyl group will be added. So will be substituted. So at high temperature, we'll get isopropyl benzene. CH3. There's another method to introduce the N-propyl group. We can treat benzene with cyclopropane. Cyclopropane gives an N-propyl benzene. The next drawback is that sometimes there is a possibility of over-alkylating. So it is not always possible to stop the reaction at the stage that we want. So let's say we have benzene reacting with CH3Br, anhydrous AlCl3. Our desired product is toluene, right? But if the reaction does not stop here, we are not able to control it at this stage. This can further react with another molecule of CH3Br and give us a di-substituted product. So we can have xylene or ortho or para-xylene can be the product, but our desired product was toluene. That is a drawback of Friedel-Crafts alkylation, that we sometimes over-alkylate the benzene molecule. The third drawback is the presence of meta-directing groups. So if there are meta-directing groups, we have already spoken about this and we'll talk about meta-directing groups in brief at the end of the video. So if a deactivating group is present on benzene, it inhibits the reaction. So much so that you need to know that nitrobenzene and acetophenone do not undergo Friedel-Crafts reaction. These groups deactivate the ring so much that you cannot introduce an alkyl group in these molecules. Similarly, in the case of benzoic acid, COOH. COH is also a metadirecting deactivating group. Furthermore, the COH group reacts with AlCl3, and benzoic acid also does not undergo Friedel-Crafts alkylation. Similarly, if you talk about aniline, NH2, aniline forms a salt with AlCl3, and then what happens is the nitrogen atom acquires a positive charge. This converts this group into a deactivating group, and hence aniline also does not undergo Friedel-Crafts reactions. So these are the drawbacks of Friedel-Crafts alkylation. Let us see what Friedel-Crafts acylation is now. Next, fifth, Friedel-Crafts acylation is introducing an acyl group, that is COR group in benzene. So if benzene is treated with acyl halide in the presence of AlCl3 or acyl anhydride, get this as the product. We'll take an example. Benzene with CH3 COCl, AlCl3 gives acetophenone as the product and HCl. And if we treat benzene with acid anhydride, this group will get substituted here in the presence of AlCl3, and we will get again this plus CH3 COOH as the product. So this is Friedel-Crafts acylation. Apart from these, other alkylating agents in Friedel-Crafts alkylation. So we have already started about alkyl halides. Aliphatic alcohols can also be alkylating agents. Aliphatic alcohols, alkenes and ethers. These can also be the alkylating agents in Friedel-Crafts alkylation. In Friedel-Crafts acylation, other acylating agents we have acyl halide, acid anhydride, carboxylic acids and esters. These can also act as acylating agents. If we talk about the metal catalyst, there are two types of catalysts that are possible. One are the Lewis acids, which are metal halides. So we've already talked about AlCl3. We can have FeCl3, SnCl4, SpCl5, ZnCl2, or we can have protonic acids like HF, H2SO4, H3PO4. So if you ever get a question where any of these apart from AlCl3 are used and the alkylating or the acylating agent is, apart from alkyl halide or acid chlorides, you can just figure out that it's a Friedel-Crafts reaction. Now we need to see the mechanism for electrophilic substitution. The mechanism of electrophilic substitution has three parts. First is generation of an electrophile. The second is formation of a carbocation. Which is also called the sigma complex or the arenium ion. Third is the removal of proton to form the product. So let us see the generation of an electrophile. First, in the case of nitration, the electrophile is a nitronium ion NO2+. This is formed by a reaction between H2SO4 and HNO3. What happens here is H2SO4 acts as an acid, HNO3 acts as a base, and this is a simple acid-base reaction like this, where we get plus HSO4 minus. Now since OH2 is a very good leaving group, water leaves here and we get nitronium ion as the electrophile. Alright, so first step in nitration is generation of the electrophile, which is a nitronium ion. It is formed like this. In the case of chlorination or bromination, the electrophile is a chloronium ion or Br+. So we have chlorine which reacts with AlCl3, which gives us Cl plus and AlCl4 minus. Similarly, bromine, FeBr3 if you want to write, we will get Br plus Br4 minus. Sulfonation is something we will discuss in the end. We will skip to Friedel-Crafts alkylation and acylation. So, in the case of Friedel-Crafts alkylation, CH3 plus is our electrophile. We have CH3 Cl plus AlCl3. This gives us CH3 plus, which is the carbocation, and AlCl4 minus. And for acylation, we have CH3COCl. The electrophile is CH3CO, a positive charge on the carbon atom. This reacts with AlCl3 and it gives us CH3CO plus AlCl4 minus. So these are the electrophiles. The first step is generation of electrophile. The second step is the generation of a carbocation, which is called a sigma complex or an arenium ion. This again we have studied in detail. You will find that video in the description below. So we have benzene, hydrogens here, an electrophile attacks benzene and we get He and a positive charge here. This arenium ion is resonance stabilized, and this is the carbocation which is no longer a planar structure because this carbon atom is sp3 hybridized now. In the third step, from this arenium ion, if we talk about nitration, we had HSO4 minus an ion. This will abstract a proton and we will get plus, electrophile here was NO2. Okay, get H2SO4. In the case of chlorination, bromination, pre-Tufts alkylation and acylation, we had AlCl4 minus as the anion that will abstract the proton. And we will get the substituted benzene and AlCl3 plus HCl. Here the electrophile is either NO. In this case it is NO2. Here it can be CH3 or COCH3, chlorine or bromine. Now for sulfonation, the mechanism is still not established and it is a topic of considerable deliberation. Lot of studies have happened and there are many mechanisms which are suggested. The one thing that is common in all of them is that SO3 is the active species. So one of the mechanisms that is suggested can be written like this. Plus SO3 gives us the selenium ion, SO3 minus. This then loses a proton to form this and this plus H plus, and then this gives us this was SO3 minus, the benzene sulfonic acid. So this is the mechanism. There are 3 steps, and for all the reactions that we have studied, we have broken down those steps and written them down here. Apart from this, benzene also undergoes addition reactions. The 2 addition reactions that are in your course are addition of hydrogen, and the second one is addition of chlorine. So hydrogen adds on here under high temperature and the presence of a nickel catalyst. Hydrogen adds on to benzene to give us cyclohexane. Nickel catalyst thing. We get cyclohexane here, and addition of chlorine, where in the presence of UV light, chlorine adds on to gives benzene hexachloride, or which is also called Gamax. So we have benzene 3Cl2 in the presence of UV light. Alright, the last reaction that we have to study is the combustion reaction. That is a very simple reaction when benzene burns in air. So we have benzene, which is C6H6 plus O2, which gives us CO2 and H2O, just like the aliphatic hydrocarbons that we have studied. Balancing this is very easy. You start with balancing the carbons first. There are 6 carbons in benzene. So 6 comes here. We have 6 hydrogens on this side. We have 2 hydrogens here. So you add a 3. So we have 6 hydrogens this side. Now count the total number of oxygens. We have 12 plus 3, 15 oxygen atoms here. Here we have 2 oxygen atoms. So if we multiply this by 15 by 2, we'll get 15 this side. So we'll just write 15 by 2. So we have C6H6 plus 15 by 2 O2 gives 6 CO2 plus 3 H2O. Similarly, you can find out the reaction of combustion of other arenes. This is it for the chemical reactions. Next thing that we have to see is the directive influence of the functional groups. This is a topic that we have in detail covered in another video. We will find that video in the description below. So what happens is when a single group is introduced into benzene. So you get a mono-substituted product, there is no confusion. But when a group is already present in benzene, then the incoming group can either be an ortho product, a para product, or a meta product. What has been found is either we get a mixture of ortho and para products or a meta product. This depends on the kind of group that is present. Okay, so there are two types of groups. One are ortho and para directing, and the other are meta directing groups. Can we make this big? Yeah. Okay, so the ortho para directing and meta directing groups are based on their R and I effects, which are their polar effects. R and I effects, resonance effect and inductive effects. It has been found that if a group has a plus R effect or a plus I effect, it increases the electron density at the ortho and para positions, and hence these groups are ortho para directing and they are activating. Activating groups means that the reaction will be faster than it is in benzene. So if there is an activating group present on benzene, the reaction will take place faster. The electrophilic substitution reaction will take faster than it would have taken place in benzene. Now, if there are groups which have a minus R or a minus I effect, this means that they pull away electron density from the benzene ring, making it less electron rich, and these groups are meta directing and deactivating. They are meta directing because they decrease the electron density because of the minus R effect on the ortho and para positions, which makes the meta position with respect to the ortho and para positions electron rich. That is the reason, and the resonance structures can be drawn for this. All of this has been covered in the video already. These are meta directing and they are deactivating because the reaction will be slower than it is in benzene. Let's take some examples. If we have phenol, OH, in phenol, because of the lone pair of electrons present on oxygen, this has a plus R effect. But oxygen is also electronegative, so it has a minus I effect also. In this case, it is observed that the plus R effect of OH group is greater than the minus I effect, which makes OH group ortho para directing as well as activating. But if we talk about chlorobenzene, chlorine also has lone pairs of electrons. So chlorine also has a plus R effect here. Chlorobenzene has a plus R effect. Chlorine is electronegative, so it has a minus I effect. But in the case of chlorobenzene, the minus I effect is greater than the plus R effect. So though chlorobenzene, a chloro group is ortho para directing, it is slightly deactivating. Slightly deactivating. We can also see NH2, NHR, NR2, OH, NHCO, CH3, OCH3, in all of these halogens and alkyl groups are also ortho para directing groups, whereas NO2, CHO, COCH3, COH, aldehyde group, ketone group, SO3H, SO2Cl, CN, CCl3, CF3, NH3, where nitrogen has a positive charge, are all meta directing groups and deactivating groups. So that's it for today. We have talked about monocyclic aromatic hydrocarbons, their preparation, their properties, and why benzene undergoes electrophilic substitution reactions. Thank you so much for watching. I'll see you in the next video.